Welcome back to this session. We are going to have our second public talk by Eric Bonnetier of Université Grenoble-Alpes. He's going to talk about. Are you going to do the talk in Spanish? I see you have a. You evolve in a random way. Okay. So, propiedades espectrales del operador de Neumann Poincaré. Welcome.
Can you hear me? Okay, good. Yes, no? No? Is that on? Turn on. Okay. Can you hear me better? Maybe I'll put this thing. And here? Still no? And I'll try to speak up. Okay, so this is a public lecture. And so at the start of, when we were trying to organize this conference with Pepe and Jean Vacher, we had thought that it would be interesting to have also conferences for a larger audience and the people interested in data science. And particularly students. And so we decided that it would be nice to stick also with the program 2 lectures that would be called public lectures, and this is one of them. And but it's a difficult exercise because these lectures actually have been embedded in the rest of the workshop. Also, the constraints are not the same. So, for instance, Jean Vacher asked me if I could give my talk in Spanish, which I'm not too comfortable with, but if you insist, I could try. At least I tried to write my transparencies in Spanish, and so I apologize for all the mistakes and the grammar mistakes and that I'll make. But if you allow me, I'll try to speak English. I'll be more comfortable with that. So is it okay with you? So the second hurdle for me is that I'm not at all going to speak to you about data. This is intended more as a, let's say, colloquial talk about my own research. And it wasn't just to, the intention was not to put my work in focus. It's just that I wanted to participate in this workshop just as my colleagues and deliver a lecture also, and not just sitting comfortably in my chair. So here's what I'm going to talk to you about. It's called Spectral Properties of the Neumann Poincaré Operator. And essentially my talk has 2 parts. In the first maybe half hour, I'll try to tell you a little bit about why we are interested in this, in this operator. So this part that I call motivation. And I'll give you a few examples where this operator will actually come into the picture. And then I'll tell you a little bit about the spectral properties and why we're interested in studying the spectrum of this type of operators. And so there will be a little bit of analysis in this part. So to start with the subject, I chose three problems that essentially come from material sciences where this operator will pop out. And the first one is about plasmonic resonances of metallic nanoparticles. And this is illustrated here with this picture where you see little glass containers that contains a solution of golden particles in water. And you see different colors. It goes from red to some kind of blue, purple, and this is actually just due to the sizes of the particles. So you have the corresponding size in the drawing, in the picture underneath. As the larger the particles, the more pronounced the shift towards blue. And this happens under certain conditions, and essentially to give you to give you what these conditions are, the particles have to be small. And here they're in the range of between 20 to about 100 nanometers. And what you see actually is a result of an interaction of visible light with those particles that, and the light will excite the free electrons at the surface of these particles and generate resonance phenomena. And this resonance phenomena will concentrate part of the electromagnetic energy and actually will deprive the incident light when you will see the light reflected. Part of the spectrum will be actually absorbed around the particle and converted to heat. And so what you see is actually visible light minus whatever has been absorbed. And essentially, this will, some frequencies of the incident light are not going to be reflected. Okay. So you can imagine the same sort of resonance phenomena in devices like that. So these are plates of silicium on which you have deposited little islands of metallic particles. And people are trying to play with the shapes and with the with how you tune these things to obtain resonance at precise frequencies. What is interesting for the applications, and I think I'll say that in my next transparency also, is that this resonant phenomena actually concentrate the electromagnetic waves around the particles. And so you will have concentration of light, essentially, in areas which are very tiny and particularly which are smaller than the incident wavelengths. And if you can concentrate sufficient amounts of energy around us in so small areas, then you can have those devices interact with molecules, for instance, or objects that are about the same order of length. So this is why there is a lot of interest for applications, in applications to use this sort of phenomena and to try to control how you can localize light in small areas, spatial areas. And applications are, for instance, biosensors, where you will try to identify single molecules. There are things also where people think of using these features in therapies against cancer, where you would send some of these particles around zones where you have cancer cells. And by shining light on these particles, you may heat them up, and the heat might allow you to destroy the tumors cell by cell, if you want. And you can do that in a controlled way at the resolution of the size of the particles, so that at orders of 50 to 100 nanometers. Okay, that's the idea. The principal ingredients for this phenomena to occur is that the particles should be somewhat smaller in diameter than the incident wavelengths. And typically for natural light, you would be in ranges that are smaller than 100 or a few hundreds of nanometers. And these are things that we can now control. We can produce particles in a controlled fashion to have to monitor the sizes correctly. And then there is another things that should come into play in terms of the modeling. Underneath are the Maxwell's equations. Maxwell's equations have coefficients, and these coefficients in the particles have to be negative somehow, which is a situation which is not a natural situation, but for some ranges of wavelengths, metals in particular may exhibit behaviors that are very close to these things. And I'll come back to that in a few slides. So just in terms of modeling, imagine that the particle occupies a domain D, which is smooth and bounded. This can be set in R3, but I think I wrote everything in RD, so D can be 2 or 3. Imagine the particles actually has size delta. You have rescaled a fixed reference domain D. So delta is a small parameter. It is centered at some point Z in space. And you want to solve the governing equation, which would be the Maxwell system, but if you want to simplify a little bit the model, you can start with the Helmholtz equation. So Laplace U plus some coefficients time U is equal to 0. There is no external field. And the coefficient here is a combination of the permeability, which we'll fix to be equal to 1, and this coefficient epsilon, which is the dielectric permittivity. Omega is the frequency. And so this equation has to take place in the particle and also outside of the particle. And at the boundary of the particle, you have a certain number of constraints to respect. The field epsilon times u should be continuous across the jump, across the boundary, sorry, and its normal derivative also should be continuous. And then at infinity, you may impose some sort of boundary condition, which will take to vanish. So essentially, here you have a system. You have say an elliptic partial differential equation where you have no forcing term, you have no source term, and usually you expect that the only solution to that system, if the system is well posed, should be 0. In case of a resonance, actually, you're looking for values, you're looking for situations in which you have many solutions to that. So you have solutions that exist without injecting any energy in the system. Okay. That's what we are looking for. And just a word about this coefficient here, which would be the salient feature. It is a positive constant outside of the particle, and it's some complex number. So that comes from physics. This is what physicists call the Drude model, which describes the behavior of metals in the range of frequency, which is of interest to us. As you can see, it's a complex number. It depends on the frequency. And actually, it turns out to have a negative real part and a small imaginary part in the range of frequency that we are interested in. So as such, this operator, when the imaginary part is non-zero, it is a well-posed problem. This equation has a unique solution, and it would be 0 because I have no forcing term. But in some situation when, and that's what we're interested in, when the imaginary part gets small, then you may pick up solutions to that which correspond to resonances of the operator. Okay? So that's the context. And you're interested in which frequencies actually lead to non-zero solutions of that system. So I told you this happens when the size of the particle is small, so this parameter delta should be small. So you can rescale the just by a simple change of variable, rescale the PDE, and you see that essentially you have the second order term with all the derivatives on the rescaled solution U tilde, and the first order term comes with a delta square when you work in R2, would be delta Q in R3, essentially telling you that asymptotically when delta tends to 0, this term should disappear somehow, and you can actually justify this asymptotic, and end up with studying this equation here. So I've changed a little bit things that here little u, the functions that govern the system is actually the permittivity times the capital U that came from up here. And this is the equation that you end up with asymptotically. So it's a simple conduction equation with a coefficient 1 over epsilon, which is equal to a positive constant outside the particle, and which is equal to a complex number which has a small imaginary part and negative real part inside the inclusion. And you want to study the solvability of this type of problem when, and what happens when, what happens as in terms of the frequencies, and for which frequency do you have non-zero solutions to that equation. And to do that, you can use potential theories. That is, you may want to represent the solution through a layer potential. That is, pick up the fundamental solution of the Laplacian, the Green's function, and multiply that by some function phi that lives just on the boundary of the particle. And this provides a function which I call single layer potential phi, which is a function which is harmonic inside the inclusion and outside the inclusion. So essentially, it will satisfy this equation inside and outside the inclusion. And what you have to check is whether this function here will satisfy the jump conditions across the boundary of the particle. It does satisfy the continuity condition, that's the properties of the single layer potential. But the single layer potential has a jump, or its normal derivatives have a jump across the boundary, and this is all classical potential theory, and which tells you that essentially there is a Dirac mass that you hit when you cross the boundary. And you have these relations for the normal derivative of this function when x is a point on the boundary of D. As you see, when x is on D, for instance, if you use kernel in 2 dimensions, you have a point where the kernel becomes singular, and this is what triggers this jump condition. Okay, so when you write down what is the transmission condition for the normal derivative, you will use these jump conditions where comes an operator which I call k star d, which has this form. It's essentially the normal derivative of the Green's function with respect to that variable times the layer potential phi, and you write down the corresponding equation. You arrive at an integral equation of that form. So the potential phi will be a solution to the Helmholtz equation, provided it satisfies this equation here. So you've changed from a PDE point of view to looking for a solution U, which is defined in the whole space, to a function phi. Oh, sorry, I have a hard time with that thing. A function phi, which is just defined on the boundary of the particle, and you have an equivalence. That is, if you can find phi, you can find U, and vice versa. So here, this lambda is just a constant and is associated to the material contrast. So it is the conductivity inside the particle plus the conductivity outside divided by twice the conductivity inside minus the conductivity outside. And so in terms of what are the relevant parameters in my problem, here I'll have something related to the shape of the inclusion, so also to the resonance phenomena that I want to capture, but also to the material contrast here. So this operator here is the one that is of interest to me. This is a Neumann Poincaré operator. And as you can see, it comes up very naturally in this problem. And what do we know generally about this operator is that if the inclusion is smooth, if its shape is smooth, then this operator is compact, and it's a spectrum, and the spectrum actually only contains eigenvalues. There is no continuous part of the spectrum, and the eigenvalues actually converge. You have a sequence that converges to 0. So that's classical operator theory. But there are some things that we don't quite know very well at this stage, is that if the inclusion has a boundary which is Lipschitz, for instance, if you have a particle like a cube, then you have continuous spectrum. And that's a difficulty that is still under investigation. But essentially also what we know from classical operator theory is that the spectrum of the operator is contained in the, it is real, and it's contained in the interval -1/2, 1/2. All right, so that was for this plasmonic resonance application. And essentially, the name of the game there is find out what shape you should give this. What would be the shape of D if you want to have particular resonance frequencies at fixed values of the frequencies. And there are a bunch of colleagues that are actually working on this type of problems. Okay, second type of application where we'll see the Neumann Poincaré operator, which is very much related to the first one. This is about cloaking, cloaking by what is called anomalous localized resonance. So I think a number of you have seen or have kids that have seen the Harry Potter movies, where you have this cloak that makes you where you can achieve these sort of things by using what is now called the metamaterials. And essentially these are dielectric materials with, these are materials with permittivity and permeability, that is the coefficients that characterize the materials from the point of view of Maxwell's equations, coefficients which are negative, which do not exist naturally, but that you can build essentially by fabricating composite materials. So, and this is a topic that is probably 10 years old, and people are investing a lot of efforts to actually come up with structures that have these properties. And to achieve or to build such structures, again, you may have to restrict the range of frequencies that you will use, and essentially this is the overall subject that concerns is propagation of waves in metals and with possibly certain ranges of frequencies. So let me focus on one applications of metamaterial, which is called cloaking by anomalous localized resonance. So the idea is like that. Imagine you have the whole space, for instance, in 2 dimensions, and look at an annulus of materials that has conductivity -1 plus a small imaginary part. And the conductivity inside the annulus is equal to 1, the conductivity outside is equal to 1. And imagine that F is a source term with compact something localized somewhere here. And you try to solve the conduction equation that will tell you what is the voltage potential corresponding to the source that you apply here, and how does it distribute in the whole space with the proper behavior at infinity. And with the conductivity, again, which is equal to 1 inside and outside the device, and which is equal to -1 plus a small imaginary part. The small imaginary part, actually, from the physics point of view, relates to the dissipation inside the metal, essentially the Joule effect and the dissipation by heat. And here's the name of the game, is what happens is this, this S, the size of the imaginary part tends to 0, which will happen under certain conditions. And essentially what you want to find out is what happens to, so fixed compact set somewhere away from your device, and look at what is the amount of electrostatic energy which is concentrated in this set. And look at this quantity when the parameter S tends to 0. So what happens is that depending on where the support of this function is, and depending on the geometry, on essentially the 2 radii of the annulus, what happens is that this energy may tend to 0, or may tend to infinity, depending on how things are. And what is particularly interesting is that for some geometric features, this thing may tend to 0 if the support of F is within a certain distance from the device, which is actually a way of hiding the source from an observer that would be sitting in this set capital A. So in a certain sense, you have cloaked the source. For an observer that is looking at your system from capital A, it doesn't see anything. It sees just if the medium was completely, just if the medium were a homogeneous uniform medium with conductivity 1. Okay. And of course, you may imagine the kind of applications that would interest, for instance, DARPA about these things, and other philanthropic institutions. So here it is, when S tends to 0, it's a system where you are elliptic outside, hyperbolic inside. Okay? Or actually, in this case, you're also elliptic inside, because the corresponding matrix in terms of operator is a diagonal matrix, but you have the wrong sign, in a way. But to make the story short, this type of PDE is actually usually through a theorem, the Lax-Milgram theorem, that tells you that this is the well-posed problem, essentially saying that when you take integral of epsilon grad v square, this defines the norm on the space on which you want to invert the PDE. But this requires that epsilon should be strictly positive. Right? Now you're in a situation, so you can manage when epsilon is complex with a non-zero imaginary part, but you're in a situation where epsilon asymptotically will be negative. And there might be certain values of epsilon for which the system is no longer invertible. Okay? This is a mechanism that causes a blow-up. Okay. Again, you may look for a solution to that PDE in terms of layer potentials. So this would be the harmonic part that is generated by the source term, and then you're looking for layer potential that lives on the external radius of the annulus and one that lives on the internal radius of the annulus. So this provides a function which is harmonic inside and outside the different regions, and that satisfies the continuity conditions across the interfaces, and you just have to verify again the jump conditions to to get something that will be a solution to the PDE. And when you write down the jump conditions, you end up with a system like that, which is an integral equation of the same type as I had before, except that you have two layer potentials. So essentially, it's some constant times the identity plus an operator is equal to the data. Okay. And the name of the game, again, is what can you say about this operator? When can you invert it as the parameter s tends to 0? And just is to show you what is the impact of this thing. So this is a plot of the solution to an equation like that when you have some small value of s. So the system is non-degenerate. Here the source is a dipole. You see the two little lobes maybe if you're close enough. And what I wanted to show is that what is depicted here is the intensity of the gradient of the function v. And what you can see is the gradient actually, the high values as the dark values, and they actually concentrate around the boundaries of the annulus. And essentially what happens is that the interaction between the source and the negative material or quasi-negative material here produces large oscillations and large values of the gradient. And so you have this phenomenon of concentration and localization of the field, and actually enhancement also of the electromagnetic field. Okay, I have to speed up a little bit. So another context in which this kind of problems might appear is related to studying stress distribution in composite materials. So here you have three pictures of different types of composite. This is wood, this is some sort of aggregate of I don't know what, this is some sort of polycrystal, where you see essentially inclusions embedded in a different phase. What is of interest to us here is when does this type of material break, and under what conditions can it break? And particularly, the questions that we want to address is that, as you see here, you have regions where inclusions may touch, or where it could be a small neck in between inclusions. And the questions we wanted to understand is whether these are areas where gradients are likely to be very large and be susceptible to actually cause fracture in your samples. This is pretty much what I say here, so I think I can speed up there. So the type of model problems that we studied is a case of two inclusions which are smooth. That's an important feature in our analysis. So imagine they are of size 1 and they're separated by a distance which I call delta. And again, you're looking for a solution. So in the simplest case, you look at the conduction equation, but you can think of linear elasticity, for instance. You look for solutions to this PDE where the coefficient A, the conductivity, is equal to 1, say, outside of the inclusions and some value K inside the inclusions. And you impose some source terms so that you produce a non-zero solution for. So for instance, you may fix a harmonic function h and ask that u should look like h as you go to infinity. And this defines a well-posed problem that you can, for which you can show existence of solutions and so forth. And the question is, how does the gradient of u behave in this area as delta tends to 0, as the things come close? And again, you can introduce single layer potentials. So you introduce a function phi1 that lives on the boundary of this set, the function phi2 that lives on the boundary of this set, with which you will be able to represent the solution of the PDE. And again, this produces a harmonic function inside the inclusions and outside. It is continuous across the interfaces, and the only conditions that you have to enforce to make this a solution is that the normal jump should be equal to 0. So the jump of the normal derivative should be equal to 0. And this you can explicit because you know what the jump is, how the normal derivative of the single layer potentials jump, and you will end up with an integral equation that will appear on my next transparency, and which is associated to this operator here, and to some coefficient lambda, which again is the material contrast between what is inside and what is outside the inclusions. So you get to this integral equation here. So data, lambda, that is the material coefficients, minus this operator k star. This is again the the Neumann Poincaré operator, times phi1, phi2 is equal to some data. And the name of the game is analyze this operator and try to see under what condition you can invert this thing, and you can study the dependence of phi1 and phi2 with respect to the parameters of interest. And what is nice in this setup is that there are two parameters. One is hidden here in the material contrast. This is parameter k, the rigidity of the inclusions, if you want. And the other one, the distance, is embedded in the definition of the operator. So in a certain way, we have separated the two main, our two main features. Okay. So just to give you an idea of what these integral operators look like, you see that, so this is the, here I've explicited one of the, so here I have a system of integral equations actually, and I've written what this operator looks like when you have parametrized the boundaries of the inclusion by some function psi1 for the first one, psi2 for the second. And this is the type of kernels that you have to deal with. You see that it's singular. It is singular when delta is equal to 0 because there is a point where x is equal to y, and this thing will vanish also at the contact point. But as soon as delta is strictly positive, this is bounded from below, and you get very smooth operators, smoothing operators that provides, that maps L2 functions into C infinity functions. And the whole point of our analysis is to understand how these things degenerate as delta tends to 0. Okay, I have some homework for you, and just to show you that. So this is a movie that was shown at a nanofilm festival at Berkeley a few years back, and made by these two persons, Baz and Alice. And it's about how you could design a bow tie antenna. So it's two pieces of metal which are close one from another, and you try to have this radiate energy, and you will see what the kind of experiments they will perform. There is a music track, but I'm not sure it will be. So what they took, they make a first experiment where they place a grain of grapes inside a microwave oven and light the oven, and as you've seen, nothing happened, which calls for some more thinking. And now what they do is they take this piece of grape and they cut it. You have to dry the base so that no water, you don't form a water film in between the grain, and you put them one very next to each other, forming exactly like my picture before. And this is what happens when you light the microwave. And it works. It works, and it is nice. You can try it. And so if you do that at home, it is wise to put a glass over the grapes to prevent the plasma that is being formed to reach the sides of the casing of the oven, because then you may damage your equipment. So be careful with that. It does work very well. You have to make sure that the grapes are somewhat dry, as I told you before. You can try with tomato. You can try with different things. What happens actually is exactly the type of things that... So what happens is the things that we are interested in. You have two conducting inclusions, the two half sides of grapes. Essentially, grapes is water, so it's very conducting. They are very close from one another. So you're in a context where the material contrast, that is the conductivity inside the grapes and in the air outside, is very large. And the distance between the grains is very small. And that creates very high gradients. So the electromagnetic fields are very high and intense in the little neck between the grains. And that actually triggers ionization of the air. And that is the cause of the plasma that you can see. Okay. This is the experiment. You can make it at home. Kids love it. Okay. So I should probably speed up. But in any case, how can we see that from our understanding of this integral operators that I'm proposing? Essentially here I'm focusing on the situation where you have two inclusions that are distance delta from one another. But a lot of this can be applied also to the other situations of plasmonics that I've shown you before. So essentially, you want to solve this integral equation. This is data, you know it. This is the material contrast, and this is this the Neumann Poincaré integral operator. And you know that when delta is strictly positive, you have an operator that is compact, so it has eigenvalues that cluster around 0. And if you could diagonalize this operator with eigenvalues and eigenfunctions, which are denoted lambda and delta and phi I and delta, then essentially solving this equation amounts to representing the data in terms of the eigenfunctions and just forming, injecting an expansion of phi1 and phi2 in terms of the eigenfunctions inside this the operator, using the fact that you have to dealing with eigenfunctions of these things, and dividing by the corresponding weight that pops out. So essentially, you can write out what the solution is. And as you can see, essentially, if this is a nice function, you have all the reasons in the world to expect that this expansion is nice and controlled. The coefficients are bounded in the way you want. So essentially, this phi1, phi2, which are closely related to the gradient of the solution U to the PDE, this phi1, phi2, essentially, if they blow up, it's not because of this guy. It shouldn't be because of this guy. Essentially, it should be because of this term here. And that's actually what happens. So if you see what these two lambda and delta correspond to, lambda is the material contrast. So lambda is something like k plus 1 divided by 2 times k minus 1. So if k is a physical conductivity, it's a positive number, and lambda is in absolute value always bigger than 1/2. The lambda and deltas, they are the eigenvalues of these operators, and I've told you before, we know that these guys, they live inside the interval minus 1/2, 1/2. So if you want to have an explosion here, you have to have both lambda comes close to 1/2 or minus 1/2, and similarly, you want the eigenvalues or some eigenvalues to come close also to 1/2 and minus 1/2. Okay. There are a few technical difficulties, though, because this is fine provided that actually the eigenfunctions form a basis, a Hilbertian basis for the operator. However, this operator, albeit compact, is not self-adjoint. But you can make it self-adjoint by changing the scalar product, and this you can do using an identity which is called the Calderon identity, which essentially amounts to redefining the scalar product in terms of the single layer potential. But I don't think I have time to go into those details. But there is a very nice piece of analysis behind that, and this dates back to Poincaré, to Kahneman, to Krein, and has been revived in a somewhat recent paper by these guys that explain the whole genesis of this operator and how these properties came up. So provided you're happy with working in a space with such a scalar product instead of the usual L2 scalar product, then you have an operator which is self-adjoint. And I think I'll skip that. Back to it. Essentially, there is another feature that you may use now that you're in a self-adjoint context, is that you have a min-max principle. And actually, you can tie the eigenvalues of the integral operator to those of another operator, which is called the Poincaré operator, which acts as follows. You take a function u, which lives in the proper function space. I don't want to get into the details. And you look at how much of u is actually concentrated on the inclusions deep. And that you represent, this is a linear form, so by Riesz theorem, you can represent that as the action of an operator on the function u. And this is the Poincaré operator. And so this is a self-adjoint operator. It turns out to have the same spectrum as or spectrum that you can easily deduce from that of the integral operator. And you do have a min-max principle, which essentially consists of you measuring how much of u is contained. So you take you're minimizing and taking a max over functions u of how much energy you have inside the inclusions divided by what is the total energy of the function u. And then you can show that, at least in 2 dimensions, the eigenvalues form, you can split them in 2 families. You have negative ones, positive ones. They are all between -1/2 and 1/2, and they cluster around 0. So we have some structural information about the spectrum. There are cases where you can actually compute what's happening, and this is the case when you have, for instance, 2 disks in dimension 2, of course, and because here there is a nice trick by a conformal mapping, you can send this picture into that picture by just changing variables. So x and y are the variables in this picture, and xi would be the corresponding complex variable here. And essentially, you're trying to solve an equation of this form on that picture, which translates into the same operator here, but here you can use separation of variables, and you can essentially compute what the spectrum is, and you have all the details. And this is what it looks like. So what we are after is this number lambda n plus and lambda n minus, which are the eigenvalues of the operators. They're intimately related to the contrast, which you can get explicitly in terms of the let me go back here, in terms of the parameters of the conformal map. So all of this is pretty much explicit. And what you see is the following picture. If you plot the eigenvalues lambda here, in terms of delta, so I've put the values of lambda here, and I've put the distance delta between the inclusion on this axis. So for instance, if I cut here at this level, what you'll see is a picture that we expected from the last slide. That is, you have a lambda 1 minus, a lambda 2 minus, a lambda 3, and etc. that cluster around 0. And you have a corresponding family on the other side, a lambda 1 plus, lambda 2 plus, and so forth, that cluster around 0. But as delta tends to 0, you see that all the eigenvalues actually will converge to -1/2 or 1/2. And these are precisely the values where you expect blow up, right? But at the same time, you would have the material contrast also half or -1/2, which means that the corresponding conductivity is going to be either very large, tends to plus infinity, or very small, tends to 0. Okay? This is a mechanism. And this is what's happening a little bit in the grapes experiment. You have a contrast here which is close to 1/2 minus 1 to 1/2 because the conductivity is infinite. And then when delta is small, these things are very close to 1/2, and so these numbers get very big. Right? So what was somewhat surprising for us is that we expected first that only a few modes would actually lead to blow up. But actually, all the eigenvalues are degenerate as delta tends to 0. Okay, I don't want to bore you very much more with that. Let me just say a few words about, so we've done a number of things on that problem. In particular, we've been able to say what may happen when, instead of having a contact point, or let me say it simply, instead of having two disks, what happens when you have inclusions of different shapes, and particularly what happens when you have here a contact point, that is, when, imagine that these two things would touch, what would be the order of the contact in terms of if you have to parameterize this curve by x to some power m? So the case of disk would be m equals 2, but what will you have a different power here? So if you have contact which is flatter, for instance. And so we can analyze that essentially by using the min-max principles that I told you before, by somewhat showing that, let me actually advance a little bit. So we had a min-max principle that told us that the eigenvalues could be computed in terms of how much energy is inside the inclusion compared to what is outside the inclusions. And so as you can see here, this quantity actually is a norm on the space on which we are operating. And you can show that if you fix some number epsilon and cut out a region like the orange squares that I've designed, that I've put up here, you can define a norm which is equivalent and which is uniformly equivalent, that is independent of the distance between the two inclusions, to the energy norm, where essentially you pick up the h1 half norm of the trace of u on each inclusion, and then you pick up something which is essentially the values of the potentials up here minus the values, or the difference in potential divided by the distance, to some powers that are well chosen. So it's the square of the potential difference divided by the distance. And this forms a norm independently of delta. And with that, you can actually rewrite the min-max principle, and then you can, up to a constant, you can switch this norm for this new norm. And this new norm is somewhat interesting because then you can compare by just changing variables from that situation to the case of disks. You can compare the eigenvalues of a different contact point to the case of how the eigenvalues behave when you have disk, and you get estimates. That is that the lambda n come close to 1/2 when delta comes to 0, but before we had a square root of delta here in the case of disks, and here you see what the influence of the geometry is. Exponent m minus 1 divided by m. Okay? So we know a number of things about that. Okay, so I'm at the end of my presentation. Essentially, so I couldn't talk about data science. I don't do data science. I presented you some of the things we do in our group, and I wanted to do a little bit of publicity for that. There are a lot of very interesting things happening in the mathematical modeling of for optics these days. People are interested in a number of applications and designs that one can fabricate, and because we can master the technological process to, for instance, make very tiny devices, but in a very controlled way. And that opens up the door for many interesting questions in terms of applications, of course, but also in terms of understanding the nature of the solutions of essentially Maxwell, Helmholtz, or the conduction equations that describe how the electromagnetic fields are distributed into these devices, with some very unexpected behaviors. I told you about cloaking. You could study super lensing, for instance, or super resolution. How do you make lenses that beat the diffraction limit, with which you could actually have a resolution which is nearly infinite? From the mathematical point of view, there are a number of open questions, and there are questions in the fields of harmonic analysis, asymptotic analysis, the numerical analysis, and computational resources that you need to study these problems that are complicated, because you're in geometries that are complicated, you have small parameters, you have large coefficients. And then if I focus on this Neumann Poincaré operator, it's a nice guy. It has lots of interesting properties, and it's fun to work with that. And with that,